Friends, I have started discussing principles of electrometallurgy from the last lecture. I realized later that I kind of rushed through when I was discussing fused salts. So, I would like to repeat a few things I said in the last lecture. We had started talking about molten salts, and before that I did point out that not all molten inorganic salts are ionic. There can be totally molecular systems, there can be systems which are partly molecular, partly ionic. We are not going to talk about these, because if you want to talk about electrolysis, we need a completely ionic media. So, we are concerning ourselves with ionic mixtures, where the individual components are also ionic and the media is totally ionic. Now, for ionic molten salts, there is a very interesting model called Temkin model, which now everybody has accepted, and I like to discuss it once again. The Temkin model for fused salts or ionic melts says that in the ionic media there are two sublattices, one sublattice for the cations, one sublattice for the anions. Let us first consider a pure salt, sodium chloride. Now, sodium chloride has a crystal lattice, and a two-dimensional representation is like this, that every sodium is surrounded by, in the first order, first coordination, chlorine ions. Every chlorine is surrounded by sodium, and the other chlorine atoms come further down. So, what we can say that in the liquid state, there will be no solid order which goes into infinity, but there is short range order, that when the solid transforms into molten state, this order prevails in short distances. And in the short distances, we will have sodium ions surrounded by chlorine ions surrounded by sodium ions. This is required for the sake of electroneutrality. Now, if to this salt, that is sodium chloride, we add another salt, say potassium bromide, which breaks into potassium and bromine ions. Potassium ions can only occupy some space previously occupied by sodium ions, and bromine ion, being an anion, must find a place somewhere where there was a chlorine ion. In other words, the anions must go to the anion sublattice and cations must go to the cation sublattice. So, there are two interlocked sublattices, one for the anion and the other for the cation. And in that fused mixture, if another salt is added, the cations can only go to the cation sublattice and anions can only go to the places occupied by anions. Temkin model also says that the activity of sodium chloride in a fused mixture is defined as probability of finding one sodium ion and one chlorine ion together in the neighborhood, which means activity will be a product of the cation fraction and the anion fraction, x cation, x anion, which will be represented by number of cations in the entire mixture divided by all cations in the mixture, because this ratio will give us the probability of finding a cation in the cation sublattice, and at that point n minus 1 by all n anions will give us the probability of finding an anion in the anion sublattice, and the product means that they will be together. So, that gives us the probability. So, in a 50-50 mixture of sodium chloride and potassium chloride, A NaCl would be half, because in the entire cation sublattice 50% positions are occupied by sodium, the other positions are occupied by potassium chloride. So, it will become half, but when we come to the anion chlorine, there is only one kind of anion, chlorine. So, the probability of finding a chlorine in the adjacent site is always 1, there is no other anion. Therefore, the activity of sodium chloride will be half, but the situation changes if we have a 50-50 mixture of sodium chloride and potassium bromide, because in this case the cation fraction, that is sodium ion fraction, is half, because half the positions are occupied by sodium, but the anion fraction, the chlorine, is also half, because the other positions are occupied by bromine ions. So, A NaCl would become 1/4. Even though there is 50-50 mixture of sodium chloride and potassium chloride, in the fused mixture, activity of sodium chloride is not half. In this case, it becomes 1/4 if it is NaCl and KBr. I hope you have understood this. Now, let us consider a little more complicated situation. We want to find the activity of a salt CdBr2 in a salt mixture, and this activity will be probability of finding one Cd in a cation position and 2 bromine ions in the nearby anionic positions in the sublattice. So, it will be multiplication of cation fraction and square of anion fraction, because you need to have 2. XBr gives the probability of finding an bromine ion in the anionic sublattice. Another one has similar probability, so that has to be squared. So, activity of CdBr2 will be given by atoms of Cd in the cationic sublattice divided by, not atoms, ions of Cd in the cationic sublattice, and total number of cations into number of bromine ions in the anionic sublattice divided by number of all anions to it is squared, because we are talking in probability terms. Now, the generalized expression for activity of a salt M sub n Z sub Z dissolved in an ideal fused salt mixture is given by activity term ionic fraction of M to the power M, ionic fraction of Z to the power Z, where x sub M and x sub Z are the ionic fractions of cations and anions respectively. This is the definition of the anion fractions. Let us solve a simple problem. If we have a mixture with equal moles of NaCl, CdCl2 and KBr, then activity of NaCl is ion fraction of sodium into ion fraction of chlorine. Ion fraction of sodium is 1/3, because in the cationic sublattice there are equal numbers of the cations sodium, cadmium and potassium, whereas the anionic fraction will be 3/4, because if you see there are total number of 4 anions, out of which 3/4 is bromine, 3/4 is chlorine, 1/4 is bromine. So, A NaCl is 1/4. Activity of potassium bromide would be ionic fraction of potassium into ionic fraction of bromine. So, it is 1/3 and this is 1/4, because 3 positions are occupied by chlorine, 1 position is occupied by bromine. So, activity of potassium bromide is 1 by 12. So, even though they are in equal proportion, we do not get the same activity value. What about activity of CdCl2? The expression for this is ionic fraction of Cd into ionic fraction of chlorine to the power square, because a Cd ion has to find 2 chlorine ions in the neighborhood, and each of them has this probability. So, it must be a square term. So, we get 1/3 for this, 3/4 for this. So, this becomes 9 by 16. So, we end up with 3 by 16. So, although we have these 3 salts in equal proportions in the mixture, activity of sodium chloride is 1/4, activity of KBr is 1 by 12, activity of CdCl is 3 by 16. This is a very interesting implication of the basic postulate of Temkin model. Of course, this is valid when the mixture is considered to be ideal. Very often the mixture may not be ideal, and therefore, there can be deviations from these expressions, but we will not go into this. Now, in a fused mixture, remember that which you have prepared by mixing sodium chloride, cadmium chloride and potassium bromide, the identities of these individual components have disappeared, because there is no sodium chloride there, there is no cadmium chloride there, there is no potassium bromide there. There are only ions of sodium, cadmium and potassium, chlorine and bromine. Therefore, we can also say that it is a salt mixture also of sodium bromide, cadmium bromide, potassium chloride. These are the things which you did not add, but you can always talk about probabilities of these, finding them. You can even calculate probabilities of finding CD Br together, not Br2, 1 CD, 1 Br, 1 CD, 1 chlorine neighborhood. All these activities will add up to 1, because then you will exhaust all possibilities of combinations. So, the sum and substance of saying this is that in a fused salt mixture, the activity of a component is not going to be defined in terms of its relative proportion. It may be there in 50%, but its activity may be less than 50% because of the complications of Temkin's model. But whatever I have said is for only an ideal situation. Now, what are some other implications of these observations? We see that when we add to a salt Mx another salt Ny, then activity of Mx is decreased, obviously, and this implies greater stability of Ax. By so putting another salt, we are stabilizing the other salt. Now, in electrolysis, this may seem to be a disadvantage, because when you have stabilized that combination, dissociation will be more difficult. But on the other hand, there is an advantage, that addition of Ny, however, will help lower the melting point of the salt mixture. This is an advantage, because you can carry out the operation at a lower temperature. You should know that seldom is a pure salt electrolyzed, very rarely, maybe never. We always take a salt and dissolve it in a solvent, which are other salts, and then we electrolyze. Like if you can see some compositions here, there is some typical data for electrowinning from molten salts. So, in the case of aluminum, I have mentioned it repeatedly, that alumina dissolved in cryolite, which is NaAlF3, is essentially you think that should be the system, but no, we also add calcium fluoride, we also add sodium fluoride. So, this is the media in which Al2O3 has been dissolved. The bath is very, very complex. This I will discuss when we come to aluminum metallurgy. There are all kinds of ions existing. In the case of magnesium, magnesium chloride is dissolved in sodium chloride and potassium chloride. So, we have a ternary magnesium chloride, sodium chloride, potassium chloride. The only thing we have to ensure is that when you apply the voltage to decompose magnesium chloride, sodium chloride and potassium chloride should not decompose, and they do not, because they are more stable. Titanium can be produced by decomposition of TiCl4 in a eutectic mixture of lithium, sodium, potassium chloride, means 3 chlorides make an eutectic system, the melting point goes down, and in that we put titanium tetrachloride. So, it is actually a quaternary. Barium chloride can be decomposed by electrolysis to produce beryllium. Supporting electrolyte is potassium chloride, sodium chloride. So, in fused salt electrolysis, we always try to find a stable salt mixture, solvent which will not decompose itself, and to that we will add the salt that we want to decompose. Now, we must, when we discuss electrometallurgy, define some terms, and you should know exactly what they mean. Very often we talk about current efficiency during electrolysis. By the word current efficiency we mean the theoretical current corresponding to the amount of metal deposited. You have during electrolysis produced certain amount of metal. Using Faraday's laws, we can find out what is the theoretical current requirement, and we divide it by what is the actual current requirement, because you need more than the theoretical current requirement. Into 100 will give us the current efficiency. We can put it in another way also. What is the actual amount of metal that has deposited by the current that you have used, and what is the theoretical amount that should have been deposited according to Faraday's laws. Now, what are Faraday's laws? Faraday's laws, there are 2 of them. One is more the current, more is the production of metal. So, there is a direct linkage between amount of current and the amount deposited. The second one says qualifies this statement, that the amount deposited will be proportional to the equivalent weight of the metal, and if you double the current, you will get twice the equivalent weight, but for 2 metals same amount of current will not give you same amount of metals, they will be proportional to their equivalent weights. So, again first law says if you double the current, you double the deposition of metal. Second says deposition of the metal would be according to their equivalent weights. So, for a particular same kind of current, the amount of copper that will be deposited in grams will be different from the amount of zinc that is deposited in grams, but in terms of equivalent weights they will be the same. Then there is another term called energy efficiency. Now, before you go to that, you must understand why the actual current required to deposit a certain amount of metal is always more than the theoretical current you require to deposit that amount of metal. The explanation is very simple. In the cell, there may be other reactions taking place also, which means some current is doing things which you do not want the current to do. You are passing the current to dissociate a compound, but it is very difficult to restrict the role of the current only to that dissociation reaction. The current can go elsewhere for some side reactions. So, there is wastage of current, and that is why the current efficiency falls below 100. But then current efficiency values, if you see, are always better in low temperature operations. Yeah, you see, this is the typical data for electroning from aqueous systems. For copper, it is 80 to 90. For cobalt, it is 75 to 90, which means here the rest of the current is going elsewhere. For zinc, 90% of the current is being used properly in dissociation of zinc salt dissolved in it, but the 10% is going elsewhere. But in the case of fused salt electrolysis, the current efficiency values may not be so high. They can drop to lower values, because there are chances of reactions, other more side reactions at higher temperatures. Now, let us come to the second term called energy efficiency. The word energy efficiency means theoretical energy for metal that is actually deposited, how much of energy you should have used for deposition of the metal that you have got, and the actual energy you have required. The actual energy that you need to deposit a certain amount of metal will always be more, because part of the energy will go elsewhere. We will come to that later on into 100. Now, what should be the theoretical energy requirement? It will be the theoretical decomposition voltage. Every salt has a theoretical decomposition voltage, decomposition potential, which we can find from thermodynamic data, multiplied by the theoretical current that should be required to deposit that much of metal, that we can calculate from Faraday's laws, divided by the actually applied voltage. The decomposition happens because of a theoretical value, but with that value we cannot operate in an actual cell. We have to apply higher voltages, because voltage drops take place in because of various factors. This I will discuss just now. So, we applied into I actual. So, the expression is decomposition voltage theoretical divided by the actual voltage into current efficiency. This is the expression for energy efficiency. Now, in electrometallurgy, these two terms will appear again and again. They would always ask what is the energy efficiency, what is the current efficiency. Now, let us talk about the applied voltage. During an actual operation, you have to apply a voltage across two electrodes. This voltage is more than the theoretical decomposition voltage, because there are some other resistances you have to overcome. The expression is applied voltage is sum total of 4 terms. First, of course, is the theoretical decomposition voltage, which you must exceed to decompose the metal. Then there is a ohmic drop, there is a resistance in the bath, which because of which there is a voltage drop called V sub r. Then there is that over voltage phenomenon. You will remember that I discussed that there are concentration gradients near an electrode surface, because while the cations are coming and depositing, as the current increases, the concentration profile near the electrode surface changes. So, the metal ion concentration voltage changes. If initially there was a certain amount, this was the concentration of metal ion. So, metal ion concentration gave some voltage, but when current starts passing, the metal ion concentration at the surface changes. This gives rise to deviations from the electrode potential. Another reason for electrode potential is from what happens in the surface, that after all at the surface the metal ion has to deposit. So, there is a surface reaction, and over voltage due to that is called activation over potential. So, the VO, that is over voltage, comes from both activation over potential and concentration over potential. which and this causes deviations from V d. V e is the voltage drop due to electronic resistance in the circuit. There are all kinds of electrical connections, and everywhere there is an electronic resistance that causes a voltage drop. There is also voltage drop at the electrodes, and V d, the theoretical decomposition voltage, you know, is the sum of the anodic and cathodic potentials. There are two potentials at the cathode and the anode. When you sum them up, you get the theoretical decomposition voltage. To that, you have to add whatever deviations have taken place because of activation over potential and concentration over potential. This can be calculated from thermodynamic data, the V d very easily. For example, if it is a salt MCl2 decomposing into M2 and 2Cl minus, it will be derived by adding the two electrode potentials M2 plus and Cl2 minus, and for that there is a straight cut expression like this. Now, the ohmic drop between two electrodes also is because of the electrical resistance in the circuits as well as in the electrode bodies themselves, and we express it by writing as electronic voltage drop is current passing and resistance in the circuit, which is written as 1 by conductance into d is the distance no, sorry, I am talking about the other term. No, ignore this part. We talk about the resistance due to electronic resistance in the circuit. That will be because of the circuit and also because of the resistances in the electrodes. Now, it can be shown by simple logic, the thicker electrodes will give you lesser resistance. If the electrodes are thin, the electronic resistance will be more, and also there is more resistance if they become too deep. It has been found that electrode should be thick and there should be width. The width does not matter, but depth matters. So, in an electrolytic cell, one tries to see that the electrodes are wide. This does not matter, but this depth matters. It should not be too deep, not too deep. So, there are all kinds of things to be taken into account, so that to minimize the applied voltage, because if the applied voltage is high, then you need more power, voltage into current will go up. Okay, let us end this lecture with one or two very simple problems that will make use of some principles we have discussed. Here is a problem that magnesium is being produced by electrolysis of magnesium chloride at 700 degrees, chlorine being liberated at 1 atmosphere. What is the change in decomposition potential if salt concentration in an alkali chloride is increased from 10 mole percent to 50 mole percent? Now, it should be quite obvious that decomposition would be easier when there is more magnesium chloride, when it is 50% than when it is 10 mole percent. It should be obvious, but you have to calculate that. We write the decomposition potential in this manner, MgCl2 in solution giving you magnesium liquid and chlorine gas. The decomposition potential for that can be written as V d naught, which is standard decomposition potential for pure salt minus R T by Z f. Then we have this activity terms ln AMG PCl2 and this, that is ln K. This is the equilibrium constant here. So, the expression we can ignore PCl2 because it is, we have said, is 1 atmosphere. We assume that activity of magnesium is unity because it is pure magnesium coming out. So, the expression only has activity of magnesium chloride. So, for 10% MgCl2, what will be the activity? Using Temkin's equation, we say it is mole fraction of Mg2 into the ionic fraction of Mg2 into ionic fraction of chlorine square. Fortunately, there is no other anion, therefore, this is 1. So, it becomes x Mg2 plus, and so from changing from 10% where activity of MgCl2 is 0.1 to 50% 0.5, we easily calculate that there will be 125 millivolt change. You will have an advantage. When you have the 50 mole percent, you need less voltage. There is a simple problem that one may have to deal with in a copper electrolysis plant. We are not talking about electrolysis in an aqueous solution. The problem says, question is 100 tons of copper concentrate are to be processed in 6 months, approximately, it is approximately 21% copper, 25 working hours per month, 8 hours per day, leaching is by H2SO4, estimate minimum rating, this is not fating, it should be rating, and rating means voltage and current of power supply unit for 12 cells in series. There are too many mistakes, series, given the E naught for the cathode and E naught for the anode. Now, solution will be, first we find out the processing rate. The processing rate will be 3500 kilogram of copper per month. Then according to Faraday's law, 96500 coulombs will produce 31.5 gram of copper, that is 1 equivalent weight. Hence, the deposition of this, we calculate how much of current will be required for deposition of this. We multiply this by coulombs, divide by equivalent weight, we find so many coulombs would be required. Total working time available with us in 1 month is obtained by finding out working days and hours per day, so many seconds. Hence, current I is easily found by a ratio, that this divided by that, this is the total current requirement. So, one rating is, we have found out what is the current requirement. Voltage requirement, the standard voltage requirement would be E naught cathode minus E naught anode, and which is this plus this 0.893 voltage. Now, since there are 12 cells in series, each cell would need so much of voltage. So, we multiply by 12, this will be the voltage required. Now, this is a problem we always are faced with in electrolytic plants. If you put cells in series, then the same current is flowing through all the electrolysis cells, but the voltages are added. So, you need more voltage, one current is flowing through. If you put the cells in parallel, then we can operate with the same voltage, because from two bus bars we can apply the same voltage in each cell, but the current will be more, because the main current will have to go through this, go through another channel, they all add up. So, you have a choice between using more current, less voltage, or more voltage and less current. In either case, the energy requirement will be over, but technology will be the same, but the technological requirements are different. There is one last problem I have listed here, that we have given the operational variables and other data for an electrolytic plant. the conductance of the electrolyte, inter-electrode separation, over voltages at the electrodes, decomposition voltage, theoretical decomposition. Sorry, the decomposition voltage is not this. I will correct it. The current density is given, voltage drop from cathode plate, voltage drop from anode plate to bus bar is given, current efficiency is given, equivalent weight of metal is given. We have to calculate kilowatt hour per kg of metal deposited. Actually, it is very simple, things have been listed. Total voltage drop we have to calculate. We have to calculate electricity. Sorry. Yeah, we have to calculate a total voltage drop. And actually, we are talking in terms of copper, it is not any problem. So, we can consume the calculate the energy consumed to by the steps shown. I do not want to go through them in detail. Now, I like to say at the end that in the industry they use both aqueous electrolysis as well as fused salt electrolysis. There are metals which cannot be produced by electrolysis of aqueous solutions because they are far too reactive. Now, when we are doing fused salt electrolysis, there can be a problem that we will not get the current efficiency we want, because so many things can happen. What are the things that can happen? Firstly, there can be mechanical handling losses at the electrodes, means you have got the products at the electrodes, but the metal you are not able to collect for one reason or other. So, you think you have not got the amount of metal you should have got, just because of mechanical handling problems you are not able to collect the metal, because high temperature operations have their own problems. Metals can evaporate from the cathode, like if you are trying to produce sodium by electrolysis, sodium may evaporate, escape into the atmosphere. There can be chemical side reactions, that there are some species which are getting electrolyzed other than the main salt that you want to dissociate. Then there can be another very interesting phenomenon, that suppose you are trying to produce sodium tin by electrolysis of tin chloride. What can happen is that you may end up producing sodium tin tetrachloride if chlorine liberated at the anode reacts with this to produce SnCl4, or in the cell if you start with SnCl4 and tin comes in contact with SnCl4, it may produce SnCl2. So, you can have a situation where you are producing tin, but the tin is reacting. So, no tin is deposited, or you can have a situation that you are producing chlorine, but you are not yet getting any chlorine, because chlorine is reacting if the bath was SnCl2 to produce SnCl4. So, if you start with SnCl2, you would lose chlorine. If you start with SnCl4, you may lose tin. So, in such situations, one has to take precautions of immediately taking out the anode product or cathode products. Sometimes the anode product and the cathode product may recombine, like if we are trying to produce magnesium by electrolysis of magnesium chloride. We have got magnesium, we have got chlorine, but if they come in contact they will react again and produce magnesium chloride. So, we have to have cells where magnesium, when it is produced, is taken out, separated out using a right kind of device, and chlorine is not allowed to come in contact with magnesium. If there is moisture in fused salt media, then a lot of current will be lost simply to first remove that moisture. So, we will pass current, but no metal will be deposited. Lastly, in many fused salt baths, a very interesting phenomenon takes place, that the metal is deposited, but the metal redissolves, not completely, but at least partly into the fused salt bath. See, you have passed current and you know this much of metal should have come because of Faraday's laws. Metal did get produced, but then metal redissolved into the bath. This has been studied very thoroughly, and the present theory is, of course, metal can dissolve like this, that it reacts with the bath, but we are not talking about a situation where the metal is reacting with the bath. The metal, say it is a liquid metal that has produced, can actually dissolve atomically, means can go into the atomic spaces in the supporting bath. It could be atomic or it could be molecular. Then from that state of solution, it reacts with the salt that we are trying to decompose to produce a subhalide. For example, suppose you are trying to produce magnesium chloride. We have produced magnesium. Magnesium may dissolve atomically, react with magnesium chloride to produce certain amount of MgCl. You may say such a compound does not exist, but it may exist in the salt bath. This situation does take place in some fused salt media. This will be eliminated or at least reduced very much if we have other salts in the fused salt bath. For example, if this is happening, if you add another salt or a third salt, then you will reduce the activity of the main salt you are trying to reduce, try to dissociate, because its activity must go down, there are other salts, and if that happens, this reaction will go to the left and then this reaction will also go to the left. So, we can reduce or eliminate subhalide formation by adding a second or a third salt in the fused media. This is another reason why we seldom produce a metal in a pure salt medium. We produce other things to ensure there is no subhalide formation, and because both the reactions will go to the left direction. Okay. I think I will try to wind up the discussions on pyrometallurgy, hydrometallurgy and electrometallurgy now. Last couple of lectures we have discussed principles of production of metals using pyrometallurgical operations, hydrometallurgical operations and electrometallurgical operations. All these operations need energy and all these operations have adverse effect on the environment. Now, in today's circumstances, we have to always think of ways and means of reducing energy requirements and reducing adverse impact on the environment. Now, much of the impact on the environment comes from use of energy, because if you are using energy, you are creating a problem for the environment. So, let us just quickly look at the kind of energy requirement, the energy needed for production of metals. Now, here is a table that gives the energy requirement for production of metals from their concentrates, mind you. Now, we can compare the process energy, that is what is normally required to produce the metal from the concentrate, with what should have been the ideal energy required simply to dissociate a pure compound. Now, titanium sponge, suppose we could, if we could produce it from pure TiO2, take pure TiO2, break it to produce titanium. That energy should have been just the opposite of the free energy of formation of TiO2. All these oxides are formed, we have the free energy of formation, metal plus oxygen, that oxide. If we could get the opposite energy, we produce oxygen and titanium. Now, the free energy of formation is 4.0 10 to the power 6 kilocalorie per ton, but the process energy requirement is so much higher, almost more than 20 times higher. Why are we requiring so much energy to break the compound to get the metal? The answer should be obvious, that you are not dealing with a pure compound. To get Ti, we have to treat a concentrate in which has come from an ore, which has come from the mines. So, when you are getting the ore from the mines, then going through mineral dressing processes, then going through pyrometallurgical, hydrometallurgical, electromechanical operations, whatever, to get finally titanium, you are spending a lot of energy in many operations other than that required for breaking of TiO2. That is why this energy is very high. In the case of magnesium, the process energy is 85, whereas the free energy requirement should have been met only by 5. Process energy in this case is 4, in this case is 5. In the case of aluminum ingot, almost 50% is the process energy is 49.6. Again, in terms of free energy, it is small, process energy is 12. Only when we come to compounds which are not very stable and which are found in relatively purer forms, which are easier to break, like lead ingot, that we find our process efficiency are higher. It is because, say, in the case of iron, we can get iron ores which are relatively almost very close to the Fe2O3 composition, plus the energy requirement in excess of the breaking down of the oxide is not that much. So, whereas the process energy is 5.5 into 10 to the power 6 kilocalorie per ton, from the free energy point of view should have been 1.4. So, process energy is 26%. So, what I am trying to say is that you can look at the free energies of formation of the pure compounds, but these pure compounds are not available in nature as such. The minerals are available in the form of ores and minerals, where you do not have the pure compounds. It needs much more energy, and that is why we have to spend so much of energy to extract metals from ores and minerals. However, if we can look at the secondary metals, means suppose you have produced aluminum which has gone into the consumer market, and after some time it is discarded, their aluminum is in a form from which to get again pure aluminum you will not need more energy, obviously, because you are not going to extract it from the ore, you are not going to decompose Al2O3, all you have to do is to take that impure metal and purify it. So, the unit energies for production of secondary metals would be much lower than the primary metals. By the word primary metals, we mean metals extracted from ores. By secondary metals, we mean metals extracted from scrap. So, the secondary metals come as a result of refining of the metal scrap. And here are some figures. The primary from ore for magnesium 90 units, secondary would be only 3. Aluminum, while it will be 61.5 into 10 to the power 6 kilocalories per ton. From the scrap, if we produce pure aluminum again, it will be only 3. Actually, it is only a process of refining you are going through. And incidentally, for metals like aluminum, the energy component is 30 to 40%. Much of the cost of the metal is the cost of energy. So, we have to give a lot of attention to processing of scrap. Look at nickel, primary energy 36.3 units, these units, secondary 3.8, copper 28.2, 4.6, zinc is also 1/4, steel is almost half, and lead is also similar. If you need 6.8 units from primary, and in this case this is fairly low, because lead sulphide is a unstable, is not very stable mineral, and it is easily roasted and easily reduced. But if you produce from the secondary source, it is so much easier. And metals like lead are very easy to be reprocessed. Many of the car batteries that use lead, the lead goes back and it is refined, cleaned off, and it comes back into the market. So, I think now I will conclude by saying that so far we have not discussed production of any metal as such specifically. We have gone through general principles of pyrometallurgy, hydrometallurgy, then electrometallurgy. The idea has been to produce the metal. We have not specifically talked about producing pure metal, although we do produce very pure metal in electrometallurgical operations and sometimes in hydrometallurgical operations also. But we have so far concentrated on production of bulk metal. In the next lecture, I will try to discuss principles of refining of impure metals. When there are impurities in the metal produced, how do we remove the impurities? We will quickly go through that in the next 2 lectures. Thank you.